All right, thank you for the introduction and the invitation. Okay, so before I start, let me confess. When I got the invitation for this talk, was at night and I was drunken. So, so that's why this title and the abstract is very weird. Okay, so please understand. Okay. All right, so let me start. All right, so we're gonna talk about some simple varieties. So I think this is a colloquium talk, so I will start from the scratch. Okay. Okay. All right. So let me fix my field. So the K will be a field of characteristic zero, but it's just like a field. So we not assume that K is algebraically closed, like any field of characteristic zero. And so I'm going to define the object we study in algebraic geometry. So first we consider polynomials, like a finite number of polynomials, f1 up to ft, within in n variables, so over K. And the object we study is the following, so which is called the variety. So this is just like a common source of this T polynomials. Right. So here, so I collect all the solutions of the polynomials. Okay. So that's the object we study in algebraic geometry. Okay. And in particular, the simplest one is the variety which is defined by one polynomial, which is called the hypersurface in the k to the n. So this is the affine n space. Okay. All right. And next, let me introduce the morphism between the two varieties. So you have the two affine varieties, Z1, Z2. And Z1 was in the k to the n, affine n space, and the other one is in the affine m space. So you have the map, which is like this. So you have the point, and then you have the m component in the right-hand side. All right, and here each gi is the rational functions. All right, polynomial over polynomial. Very simple. So, but I said this is a map, but it's not. To be precise, this is not a map because some rational functions not defined on a Z1. So you have some point where your rational function is not defined, right? But we call it this is a map in algebraic geometry, but we say it is. It's called the rational map, okay? Because your component is considered of the rational functions. But in particular, if every GI component function is well defined on at every point of Z1, then we say this map is a regular. This is actually a map, right? Because this map is defined everywhere, right? All right, and if this map has the inverse, which is again rational map, then we say this pi is the birational map. So the birational geometry is the study of the variety in the up to birational maps. Right? So if two varieties has the birational, which meaning is you have the birational map between the two varieties, then we say these two objects are the same. Right? That's what birational geometry is studied. Okay. All right. All right, but the affine, so our object here is in the affine space. So it's sort of like a non-compact object. So it's, in some sense, it's hard to study. So, but its compact object is the easy to study. So any kind of geometry, they always consider like a compact object, right? So here, we also consider a compact object, which a sort of a compactification of the affine variety, which is called the projective variety. So when we first define the projective space, this is simple. So you collect the, you consider like affine n+1 space, and you delete the origin, and then you take the quotient by this equivalence relation, which is this, right? So 2 points are the equivalent if and only if there is some non-zero constant which satisfy this relation. But simply this means that this will be called the projective n space. Projective n space is a set of one-dimensional subspace in the n+1 vector space. So this is exactly what that means. Okay. So this is the projective n space, and here we'll do the same. So you consider, instead of just the simple polynomials, we consider homogeneous polynomials. So each monomial has the same degree. So you consider homogeneous polynomial, and you define the same. You consider the common zeros of this homogeneous polynomials. Here, 1 point means a one-dimensional space. So you may have infinitely many representative for the points. But here, so the value of polynomial doesn't make sense. But the zero or a non-zero of the polynomial makes sense here, right? Because it's a homogeneous polynomial. So if one value, one representative of the point, if the polynomial has the value 0, then if choose the another point, then still you have the 0 value. So that's why this definition makes sense. All right. So this is called the projective variety. And the simplest one is the zero set of defined by the one polynomial, which is called the hypersurface. Okay. And if degree of the f1, as a polynomial, d1, then we say the hypersurface defined by this f1 is called the hypersurface of degree 1, d, right? All right. And small remark here is affine n space is a subset of the projective n space here as an open subset. Okay, you can simply check. All right, let me go on. All right, and you can also define the map between these two projective varieties in the same way. So, but only difference is here here GI you use the rational functions, but to be rational functions. All right, so the polynomial over polynomial, right? Rational functions, but each polynomial should be a homogeneous polynomial and same degree. Otherwise, it's not a function. It's not a well-defined function because, as I told you, each point has the infinitely many representatives. So if you apply this representative to the polynomial, it's not well-defined. You will have the different values, right? But when you have the homogeneous polynomial over homogeneous polynomial with the same degree, then well-defined, right? So that's why. So GI is the rational functions, homogeneous, same degree, right? Or you can say GI, each GI is a homogeneous polynomial of the same degree. Then it's the same because when you have when you have some expression for your rational map, then you have each component has this denominator, and you take the product of all the denominator, and then because it's this project space, you can take the multiple of the product of the denominator, then you will get this expression, right? So this is our map between the projective varieties. So I introduced the object to study, and I introduced the relation between the objects. Okay. All right. And when we define the rational varieties, so So definition is just simple. So X is rational over K. I said over K. It depends on the field. Defining field. So that's why I said the over K. If there is a bidirectional map of X onto Pn. So Pn, the projective space is the simplest variety we know, right? So like everything is clear and like, so if you have the bidirectional map from the X to the Pn or like affine space, because affine space An is the open subset of Pn. So Pn and An are bidirectional, so it's the same. So when you have the bidirectional maps to the X onto the Pn, then we say X is a rational. Right? All right, this is the one definition. Or you can define the following way. So X is rational over K if the field of its rational functions of K is isomorphic to rational function field. This is this field is the Gaussian field of the polynomial ring. Okay? And the field of rational functions of the variety K, over K, is defined in this way. So set of all rational map from X to K, one-dimensional affine space. Okay, that's the rational. The field of rational functions. Okay. All right. If the field of rational function is the isomorphic to the quotient field of the polynomial ring, then we say X is rational. Okay. All right. So this is the simple fact. If two varieties are birational, then if and only if the field of rational functions are isomorphic as a K algebra or field. Right. So if our previous definition for the rational variety was this, right? So we say X is a rational if there is the birational map of X onto Pn, right? But if two varieties are birational, then their field of rational functions are isomorphic, right? So Pn and X, but the rational function field of the Pn is just like a quotient field of the polynomial ring. So that's why this definition follows from the equivalent to the previous definition. Okay. All right. So another a simple version of the rational variety. So a variety X is rational over K if it has parameterization by rational functions defined over K. Okay. So, but without this phrase, it's true, still true if the dimension is 1 or 2. But if higher dimension, it's not true. So that's why I input this generically 1-to-1. Well, generically 1-to-1 is this map is the 1-to-1. Almost all everywhere. We say the generically 1-to-1. So this is the definition of the rational variety. But this is a very familiar concept. I think you run this concept from the calculus. So this rationality problem is not hard or it's very weird problem. It's from calculus. You see here. So I still remember this exercise in the calculus book because I was very impressed by my TA. So I didn't know how to solve this problem. So I think this problem appears in the some line integral problem. So to compute the line integral, you have to find some this parameterization, right? So that's why they provide this parameterization problems. So see here, find the parameterization of the curve. X squared is y squared is x squared plus x cubed by rational functions, right? So again, all right, so this exercise, I mean, at that time, my first question was, like, they listed all kind of like this curves. And then they asked me like to find their parameterization. So my question was like that. When you have the arbitrary, like this curve defined by two variable polynomials, how do you know like whether it has a parameterization or not? That was my question. So this is exactly the rationality problems. When you have the variety on the plane curve, I mean, when you have this curve in the R2, the question is whether it's rational or not, right? So it's right. I'll solve this problem later. Okay. So wait again. So let's generalize my naive question. So how do you know it has a parameterization or not? Right? That was my question. And so you can ask, do we have some numerical invariance? I mean, numerical invariance of the plane curve or like whatsoever, some varieties that characterize the rational varieties. I mean, if you have such a numerical invariance, it's simple. Oh, this guy has this numerical invariant, like 1 or 2 or something like this. Oh, then it's rational. If not, oh, it's not. So this problem, I mean, this parameterization problem doesn't make sense, or it has no solution. It's simple, right? All right, so let's consider this problem, I mean, this question. So from the calculus, our problem was the one-dimensional problem. I mean, we considered like this one-dimensional object, right? Curves. So one-dimensional story here. All right. All right. So here we consider smooth curve. Smooth means you don't have some a bad points, like a cusp or like this node or something like this. Everything is smooth, right? So that's suppose you have a curve like this. All right, in one-dimensional, I mean, world, you have some numerical criteria which tell us it's rational or not. That is the genus, actually. If genus is 0, then it's rational. If not, then it's not rational. All right? But it's almost true. But there's one condition here. All right. All right, so this is due to like some famous theorem in algebraic geometry, which is called the Riemann-Roch theorem. But I'm not gonna tell you what Riemann-Roch theorem is whatsoever. But it's based on this theorem. And this criterion works only when it has the k rational point. So you must have the one point in this defined over k. Otherwise, it's not true. For example, like when you may consider like let me think. Like you have like x squared plus y squared is z squared over q. Then this guy has x squared plus y squared plus z squared is 0, right? Over q. It has no k rational point. It's not rational. You don't have any bidirectional map to the P2. P1 over q. So it's not rational. So you need at least one point. Okay? So in one-dimensional world, you just check the genus. Then it's done, right? All right. And two-dimensional, like suppose you have surface, and so if S is rational, if and only if you have some numerical criterion which is consists of two numbers. So if both numbers are 0, then rational. Wait. So this criterion is called the Castelnuovo rationality criterion. It's like 100 years old, there. But this criterion works only when the field is algebraically closed. If not, then it's not true. I think of this if the characteristic P is still true, but you need the algebraically closedness.
This implies unirration.
Not sure about the characteristic P. Because it's okay. I declare when I start this. Our field is characteristic 0, and if in the characteristic 0, this criterion works only when this field is algebraically closed. Otherwise, it's not true. Yeah? I'll show you later, in which this criterion fails. All right. So let's consider the concrete example, easy one, so everybody can understand. All right. So we're gonna consider a quadric hypersurface, which is defined by degree 2 homogeneous polynomial, one polynomial, degree 2 in Pn. Okay. So here x is defined by quadric homogeneous polynomial. Okay, that's our object to study. All right, and suppose you have one k-rational point. So by coordinate change, you can assume that this point is the 1, 0, 0, 0, 0, this point. Okay. All right. So my claim is this: a smooth quadric hypersurface with at least one k-rational point is always rational over k. Okay. So let me prove. It's very simple. All right. So I have this k-rational point. All right. Then you have the point Q on your x. Then you consider the line which is defined by this fixed point P, our k-rational point, and this another k-rational point Q. Then it defines, we all determine the one line which is defined over k. All right, and I fixed the one hyperplane. Hyperplane means the zero set of the linear equation, all right, x0, and then you take the intersection with this. Then you will have the one point on this hyperplane x0 is 0. Right? That's our image, right? So this is the well defined everywhere, almost everywhere, right? All right, and I have to define the inverse rational map, right? Let me show you. All right, you choose the this is shows why this point is the rational point, k rational point. All right, let me show you the inverse. All right, I choose the one point on this hyperplane, on this one, and this shows the parameterization of our one line, which is defined by P and the one point on the plane. All right, and then you have to find the point Q, the inverse image, which is exactly this. So you put this expression into the polynomial, quadratic polynomial, then you will get what? The quadratic equation in lambda and mu, right? Because our polynomial f is the quadratic. And this f pass through this point P, right? And this line also pass through the point P. So that means, this equation must be like this. Lambda equals 0 must be a solution of this equation, right? That means F pass through this point P, right? So the other point, the other solution, mu is the minus, the negative B, and lambda is the A, right? That's another solution of this quadratic equation, and this guy define a k-rational point, right? That's the inverse image, right? Very simple. Okay? So you have a quadratic equation. You have one point on this quadratic like a hypersurface. So you project this you choose any point here on X. You take the line here, and it will hit the hyperplane, right? That's our image. And when you have the hyperplane here, when you have the point on the hyperplane, you take the line determined by this guy and this guy, and overhit the one point here because it's quadratic. And because this is a k-rational point, and the other one also must be a k-rational point, right? So that's actually the idea of this solution for this problem. So same. So here it's almost same. So here it's not quadratic because you have the cubic term, right? But this curve is like this. You have this point, which is sort of like a double point. So cubic equation has how many solutions? 3, right? In quadratic case, always 2 solutions, right? So in quadratic case, so you fix the one solution and you vary another solution, right? That's the story, right? But here in cubic case, you have 3. So you fix the one point, but still you have the two solutions. That's the problem. But here, in this case, you have the double point here. So when you vary, so here is always have the multiple root. So you have 2, and so you only have the 1 remaining. So that's why the same method works. So you have this, like this, right? You don't have 2 points because once your line passes through the double point, then you always get the 1 point, right? So you consider this guy, line, y is tx, which passed through the origin, right? And you replace this y by tx, right? So you will get the t squared x squared is x squared plus x cubed, right? And so every term has the x squared because this point is the double point. So that's why you have the x squared always. So you remove this x squared, this, then you will get t squared is 1 plus x, right? And then you replace, so x will be a t squared minus 1, and y is the t times t squared minus 1. So that's our parameterization, like this, right? I was very impressed when I was a calculus student, TA showed me this way. You see this is the double point, so that's why in that way you can easily find this parameterization. So I was shocked. Oh, my TA must be a genius. But later I realized, he learned this from some book. All right, so let's increase our degree. So we're gonna consider cubics. So when you deal with your 2, was sort of easy because once you fix the 1 point, and then you deal with the another point. So that was the beauty of the quadratic, quadratic hypersurface. But cubic, so So here I said smooth cubic, so you don't have the double points. So you have 3 points like playing each other. So even though you can fix the 1 point, you still have 2. You cannot handle the 2 points at the same time. I mean, in a simple way, right? So that's why this cubic is some kind of like a divine object, right? So like for example, whenever I teach calculus, I always like told my students like like linear algebra is like let me say it this way. So like between 2 and 3 there is a big gap. So 1, 2 is a humane. After 2, 3, 4 is divine. So like it's hard to like handle. After 2. So you will see. Alright, so first statement is this: like smooth cubic curve in P2, which is defined by cubic polynomial in 3 variables. It's a non-rational. You can always find some like a non-vanishing like a holomorphic one form here. So like that's why. But let me skip just to believe like non-rational. Okay. All right. So let's jump to the cubic surface. Okay. All right. Cubic surface is your ambient space is P3. All right. And you have like a cubic homogeneous polynomial. Okay. So 3 variables, 4 variables, and each monomial has the degree 3. Okay. All right. All right. And suppose your surface S has 2 disjoint lines defined over K. Okay. All right. Here is the method how to deal with the 3 points at the same time. So there is some way to fix 2 points. Here's the method. So L1 times L2. So L1 is the line which is isomorphic to P1, the one-dimensional project space defined over K. So L1 cross L2. All right. All right. So you choose the 2 points. One is from the L1, the other one is from the L2. Okay. All right. Then 2 points will decide one line. All right. So it determines the one line. All right. Because these 2 points are K rational point. So this line also defined over K. Okay. All right. You have a line and you have cubic surface. And these 2 points on S. So it will hit another point here. 1, 2, and 3. Right? All right. These 2 points defined over K. So remaining solution is also defined over K. Right? All right. We have one variable cubic equation. One solution is defined over Q. The other one solution is defined over Q. Then last solution must be defined over Q, right? So same reason. So here. Okay. So this is and this is the rational map. It's not defined everywhere, but defines almost all like points. So this is one direction. All right. So we need the inverse rational map. Okay, so this is our original direction. All right. So inverse map is like this. You have 1 point R on S, right? And you have this line L1, capital L1. All right. If your point R is outside of this line, Then you have a line and one point outside. All this side a plane. Right? Right? You have one plane. And you have R and the another line L2. And this couple also decide one plane, another one plane. Right? And you have these two planes, they all intersect along the line. Right? Okay? And you have a line, and you have L1 here, another line L1. All right, so you have this line and this line, which is the this line and this line is on here. All right. So this is defined by L1 and point R here. All right, and here you have L2, and this will decide the another plane, and they will intersect. I mean, these two planes will intersect along their line. All right, this is script L R. Right. All right. On this plane, this L1, capital L1, and this script L R will meet. In P2, every line supposed to meet. I mean, they always meet. So they will meet, and here, this plane, L2 and R, I mean, script LR will meet. Right? That's the each point. And that's exactly the inverse map. Okay? So that's why this cubic, where's my, here. So our cubic surface S has two disjoint lines defined over K, then S is K rational. Okay? Right? So the question is, to apply this method, you have to find your line defined over K, I mean two disjoint lines, right? So if our field K is rich enough, for example, like algebraically closed, then S has two disjoint lines defined over K. Actually, over algebraically closed field, S has exactly 27 lines. Well, I'm not saying like this 27 lines like disjoin each other, but there is a sum. Among the 27, you can choose the two lines which are disjoint. Okay? So if K is very rich, I mean the algebraically closed, for example, then you can always find the two disjoint lines on the cubic surface, smooth cubic surface. But if your field is poor, then it's not true. You can find these two disjoint lines. So for example, like if smooth cubic surface of Picard number 1, I will explain what that means. This kind of like smooth cubic surface cannot have two disjoint like lines defined over K. For example, like this cubic. So x cubed, y cubed, z cubed, 2 times w cubed defined over Q. This guy has no like two disjoint lines defined over Q. All right, so this the Picard number 1 here means is this. So every curve, I mean, defined over K on S is like a linearly equivalent to multiple of the hyperplane section class on S, which means, right. So you have the curve defined over K on S, and the hyperplane section means so like a S intersection by hyperplane, one linear equation. That's the hyperplane. I mean the hyperplane. So that means So there is some like rational function such that this guy has the 0 along the C, and it has the pole along the this hyperplane section with some order. That's what this statement means. Okay. All right. So if your field K is very poor, then the question is like, I mean, if you cannot find like a two-dimensional line, then you can ask like whether this guy is rational or not. Okay? Sometimes yes, but sometimes no. So for example, like a smooth cubic surface of Picard number 1, meaning like that, is non-rational. Okay? So you cannot find the parameterization. So if you find such like a question, like a calculus, like a problems, then you can say, oh, this problem doesn't make sense, right? All right, so why? So let me explain briefly explain how to prove this. All right, suppose it's rational. All right, that means there is a rational map from S to P2 defined over K. Okay. All right, so then from now on, like some like a technical things, so you can just enjoy. Okay. All right, so map is induced by some kind of like a mobile linear system, meaning is there is some like a rational functions which generate this linear system, the finite number mobile function, I mean the rational function. Right, sort of like the linear system is just sort of. Let me describe this way. So linear system means the setup here, like the set of the curves, such that any two pairs of the curves in this linear system is in that relation. So one is the 0, and the other one is the pole of the one rational function. Okay. All right, and so you have such like a linear system. Okay. All right, and so our like assumption is the Picard number of S is 1, means this group is generated by a hyperplane section. Okay, so this linear system must contain in this linear system n times h. Okay, for some n. Okay. All right, and if this pi is not an isomorphism, then that implies this linear system has some like a bad singularities. There's some point where this members in the linear system has the singularities. This is called the maximal singularity, and this has the long history, like more than 100, was introduced by Farner and Iskowski and Manning. I mean Nether. This Nether is not the Amy Nether. This is Max Nether, more famous than the Amy Nether. I mean, all right, in our circle. So this vast singularity means you choose the arbitrary member in this linear system, and then you measure the multiplicity at some point. Then there is some one point. Every member has the multiplicity strictly bigger than n. This n is from the others. Okay? That's the key point on this proof. All right. So you have this very bad point P, and then there is a way to like resolve this point, your singularity. So that was the introduced by two methods. I mean, it was introduced by the two guys. One is the Gaussian involution. So your S is the P2, P3, and the cubic surface. Right? You have the point P on S, right? And you consider projection from this point to P2. Right? It's like you consider a line, right? Then this line will hit the another 2 points, right? Because you fix the one point P on S. So 3 solutions, but one solution is fixed, so you have 2 points, right? So this map is the generically 2-to-1 map, right? 2 points goes to 1 point, right? So generically 2-to-1 map. So you have the involution, so you can exchange, right? The solution, right? That is called the Gaussian involution of this cubic, okay? Right? And actually there is another involution which is related to the elliptic curve. Elliptic curve is the variety which has the group structure, one-dimensional object which has the group structure. So there is some way to assign the identity. Once you assign the identity, then you can define this involution, like you send the 1 point to the inverse, right? So that gives us another involution, which is called the Bertini involution. So here we can define the map from the S to P1. So each fiber is the elliptic curve. So in that way, you can define the involution. That is called the Bertini involution. So you have on cubic surface, you have 2 kinds of involution. So one is Gaussian, and the other one is Bertini. So Gaussian from the quadratic involution. The Bertini is from the elliptic involution. Okay? Right, so let's just consider like a simpler one, like this quadratic involution. You change the solution, right? You send the one solution to the other, right? All right. So what I want to say, this involution, like this. All right. So we want to see what this involution do for our linear system M. That's what I want to explain. So here, you have the 1 point P, where the members of the linear system have their path singularities, and you consider like a tangent plane at that point to S. Okay? Then what this tau do? I mean, this is our quadratic involution. It switched this tangent space to the exceptional divisor, which is related to the tangent direction. I mean the tangent space. You have the hypersurface. I mean hyperplane section, which is related to a tangent space, tangent hyperplane section, and this tangent hyperplane section, it has it hides some tangent vector information. So they switch. So what I want to say is this. So we want to see this. So you send every member in the mobile linear system to itself by our involution tau, quadratic involution. So what they do is they reduce this number n. Okay, so it means in that sense, like it reduced the singularities. Okay, so just believe like this tau send our script m to the another linear system, which sits in the n1 times h. n1 is strictly smaller than h. Okay, so wait, reduce the degree. Right? If then you can see like this birational map. So at the beginning we consider this pi from S to the P2. That was our original birational map, right? But I composed this tau involution, birational automorphism. So tau and then pi, right? So we make a round trip on S, and then we go to the P2 along the pi, right? So that's another map, and this birational map induced by the new mobile system, but that is the exactly tau of m. Okay? And we check this tau of m sits in the n1 times h. Okay, so when you apply this tau to your linear system, every time this number n is decreased. Right? So after a finite many times, so you will get the n is 1. That means your map is isomorphism. So which is contradiction, because S cannot be a P2, cannot be an isomorphic. Okay? So that's the contradiction. Right? Right. So statement is if cubic surface of if cubic surface has Picard number 1, then it's not rational. Okay? So this is the example where this Castellover rationality criterion doesn't work. So the homological information is the same. When you change the field, it's still 0, right? But the rationality changed. Okay? All right, let's get back to the easy one. So with two disjoint lines, and on cubic surface. Okay. All right, we can generalize this. So like this. So a smooth cubic hypersurface in P2m plus 1. Okay, the higher one. More variables, but still same degree, cubic, 3. Okay. All right, then we can generalize our observation. So if X contains two disjoint n planes, I replace the line by n planes. Okay. In P3, the cubic surface case, P3, n is our P3. So our n in that case is 1. Right? So that's why one-dimensional plane, which is a line. Right? But here, 2n plus 1, then, and if X contains two disjoint n planes, then X is rational. Same reason. You can play exactly the same way. Then you can show this is rational. You can construct the birational map. Right? Right? All right. So we deal with the case when n is 1. Right? Let's consider the case when n is 2. Right? So as I explained, there are some rational cubic fourfold. The cubic hypersurface in P5, because you can find a smooth cubic that contains two planes. Right? If you have two disjoint n planes, then it's rational. Right? So that's why some cubic fourfold, the cubic hypersurface in P5 is rational. We know. Right? And so far, no single example of non-rational cubic fourfold has been reported. So it's a big conjecture. I mean, like a big open problem in P5 for the cubics. Whether like general means almost all cubics rational or not. We don't know.
You show algebraically closed?
Yeah, algebraically closed here. Okay, it's a big problem. We don't have any guess, rational, non-rational. So it's a still big problem, and I think it's far away for the proof. Okay, but smooth cubic threefold, I mean the P4 and the smooth hypersurface in P4 defined by cubic polynomial is non-rational, known to be. I mean every smooth cubic threefold is non-rational, which is proven in 72. Was a famous theorem. It's by Clemens and Griffiths. So, but the method is very complicated, and they use the intermediate Jacobian like a method. So, but it's very beautiful proof. And for smooth quartic threefold, which is the quartic hypersurface in P4, is non-rational. And this is proven by Skopsky and Manin in the same year. But the proof is exactly the same as the cubic case, the smooth cubic Picard number 1. This is called the maximal singularity method. So like what they do is that they prove if smooth quartic threefold is rational, then they must have the bad singularities, which is the maximal singularity. And then if there is the maximal singularity, and then like what they do is they find some contradiction. So that's the way to prove their way to prove the statement. It's very like effective in this area. And later, 87, the Puklikov proved every quintic fourfold. So smooth hypersurface of degree 5 in P5 is non-rational. Exactly the same method as Skopsky-Manin. Okay, I mean in a big scale, is the proof is the same line, but the details are very different. Okay, and 98, Puklikov general hypersurface of degree n in Pn, which general means the almost all. Okay, and it's non-dimensional. Same method, maximal singularity method. Okay, but details are very different and difficult. And 13, I mean like 2 years ago, Deperne, he proved every smooth hypersurface of degree n in Pn is non-rational. Same method, I mean the maximal singularity method, but they also use some jet space or those techniques, so high techs. But in a big scale, it's the same method, right? And year 2000, Corti with Puklikov, they proved there is some similar version, weighted version. I mean here. So I mean at the beginning I defined the project space. So but you can define also weighted project space and something like this. So you put here some weight here, AI. And then you also consider the variety defined on this, and then you can ask us similar questions. So there is a famous 95 families of weighted a threefold hypersurface. Okay, and they proved the general hypersurface. I mean almost all in this family is non-rational. Was 15 years ago. And recently, the Chesov and I proved every quasi-smooth means, yeah, like almost same as the smooth. So like smooth hypersurface in this 95 families is non-rational. So the method actually the same as Iskowski-Manin proof. It's a maximal singularity method, but you need some like some other high tech to follow this method. Okay. So this is not much, and still, I mean, this area is still like there's many class which need to be proved rational or not. So it's still hard problem. I mean, so if you're interested, still you have many problems in this area. So you are welcome to attack. All right, thank you.